Imagine you are a detective and solving a mystery. Before arriving at a decision, you will first look for clues, patterns, and hidden information. Data scientists do exactly the same. Before building any machine learning model, they first perform exploratory data analysis or EDA. Today, I will show how to uncover valuable insights from any datasets using Python. Hello everyone, I am Viren and welcome to my channel Data Science Decoded. On this channel, we will simplify data science, AI and machine learning concepts. In the previous video, we cleaned the dataset that we downloaded from Kaggle. But after cleaning, we still don't know what data is actually telling us. This is where exploratory data analysis comes in. EDA helps us to understand the structure of the dataset, identify the trends, and discover relationships between the variables. Let's see how EDA works through coding. Let's begin by importing the libraries we will need for exploratory data analysis. First, we import Pandas using import Pandas as PD. Pandas is used to load, organize, and manipulate our dataset efficiently. Next, I will import Matplotlib, which helps us to create graphs and visualizations like bar charts, histograms, and line charts. Finally, we import Seaborn. It is built on top of Matplotlib and allows us to create more attractive and informative statistical visualizations with very little code. Now, let's load our cleaned data set. I'm using pd.read CSV because our data set is stored in CSV format. Once it's loaded, I will save in a variable called df, where df stands for data frame. A data frame is simply a table made of rows and columns. To make sure dataset has loaded successfully, I will simply print it. This displays all the rows and columns stored inside the data frame. Before starting the analysis, let's first understand our dataset. This dataset contains 2000 house records, where each row represents a different house and each column represents one of its features. We have numerical columns like area, bedrooms, bathrooms, stories, parking, age, locality rating, and price. We also have categorical columns such as city, furnishing status, main road, guest room, basement, water supply, air conditioning, and preferred tenant. The goal of this dataset is to analyze which factors affect house prices and to discover useful patterns hidden inside the data. Since this dataset has already been cleaned in the previous video, we can now confidently begin our exploratory data analysis and focus entirely on extracting meaningful insights. Even though we cleaned the dataset in the previous video, it's always a good practice to verify that no missing values remain. We use isNull.sum. Here, isNull checks every cell for missing values and sum contains how many missing values are present in each column. The next step is checking duplicate records. Duplicate rows can affect our analysis by counting the same information multiple times. Now, let's use head. This displays the first 5 rows of our data set. It's one of the quickest ways to understand how data looks after loading it. From here, we can quickly identify the column names and get a basic idea of the values stored in each column. Now, I will use info. This provides detailed information about the dataset, including the number of rows, number of columns, data types, and memory usage. This helps us verify whether each column has the correct data type. For example, age should be numeric, while city should be stored as text. Finally, let's use describe. This generates a statistical summary of all numerical columns. Here we can see important statistics such as count, mean, standard deviation, minimum value, and maximum value. And there are also different percentiles. These values help us understand the overall distribution of the data before moving to the visualization. Now, we have understood the structure and the quality of our dataset. We are ready for the most exciting part of exploratory data analysis, that is, creating visualizations to discover patterns, trends, relationships, and the outliers hidden inside the data. Our first visualization is a histogram, which helps us understand how the values of a numerical column are distributed. Here we used plt.figure fixed size is equals to 9,4, which helps us to understand that our graph should be spread out in a region of 9 rows and 4 columns. Then we used sns.histplot, indicating that histogram will be plotted on area column. Bins 20 indicate that there will be 20 bars in the histogram. KDE is equals to true, which means we need a bell curve in the histogram. Then we gave the title to our graph, that is area distribution. Here we are analyzing the area column. On the x-axis, we have the house area in the square feet. On the y-axis, we have the number of houses that fall within each area range. The blue bars represent the frequency of houses, while the smooth blue curve called the KDE curve gives us an overall view of the distribution. From this graph, we can observe that the house areas range approximately from 500 square feet to 6,000 square feet, showing that the dataset contains both small and large properties. Another important observation is that the distribution is fairly spread out. There is not just one dominant house size, which means our dataset has good diversity in property areas. Understanding this distribution is useful because it helps us detect unusual values, identify patterns, and decide whether further pre-processing or transformations are needed before building a machine learning model. Next, let's analyze the price column using another histogram. Again, the x-axis represents house prices, while the y-axis shows how many houses fall into each price range. Looking at this graph, we can see that most houses are concentrated around the middle price range, approximately between 10 lakh and 15.5 lakh in this data set. As we move towards the left and the right ends of the graph, the number of houses decreases. This tells us that very low priced and very expensive houses are comparatively fewer. The histogram forms a shape that is close to a bell curve, indicating that the prices are fairly balanced around the average rather than being heavily skewed towards one side. This is valuable because it tells us our dataset isn't dominated by only luxury homes or only budget homes. Instead, it contains a healthy mix, making it more suitable for analysis and machine learning. Our next visualization is a box plot, which is one of the best graphs for understanding the spread of data and identifying the outliers. First, I created a new figure using Matplotlib. The plt.figure function creates a blank canvas where our graph will be drawn. Fixed size 9,4 means the graph will have a width of 9 inches and a height of 4 inches. Next, I am using Seaborn's boxplot function to create a box plot of the price column. Here, x is equals to df price tells Seaborn that we want to visualize the house prices on the horizontal axis. Data is equals to df specifies the data is coming from our data frame named df. Then I am giving my graph a title using plt.title. This doesn't affect the data, it simply makes the graph more understandable. Unlike histogram, a box plot summarizes the entire dataset using 5 important values: the minimum value, the first quartile, the median, the third quartile, and the maximum value. The vertical line inside the box represents the median, which is approximately rupees 12.5 lakh. This means 50% of the house is priced below this value, while the other 50% are priced above it. The box itself represents the middle 50% of the data, also called the interquartile range or IQR. In this dataset, most house prices lie roughly between 10 lakh and 15 lakh. The lines extending from the box are called whiskers. They show the normal range of house prices, which extends approximately from rupees 4 lakh to rupees 20.5 lakh. One interesting observation is that there are no outlier points visible outside the whiskers. This indicates that our data has already been cleaned and doesn't contain unusually high or low prices. Overall, the box plot tells us that the majority of house prices are concentrated around the middle range, making the dataset balanced and suitable for further analysis. Now, let's move to a count plot, which is used to visualize the frequency of the categorical data. Now, I am creating again a new figure using Matplotlib. The plt.figure function creates a blank area where a graph will be displayed. Fixed size 7, rows sets the width of a graph to 7 inches and height to 5 inches. Next, I am using Seaborn's countPlot function. A count plot is used for categorical data. It counts how many times each category appears in the dataset. Here, x is equals to df city means I want to count the number of houses available in each city. The data is equals to df parameter tells Seaborn that the data is coming from our data frame named df. Now I am adding a title to the graph using plt.title as city distribution. Here, the x-axis represents different cities, while the y-axis shows the number of houses available in each city. From this graph, we can observe that the Mumbai has the highest number of house listings in our dataset, followed closely by Hyderabad. On the other hand, Chennai and Bangalore have comparatively fewer houses records. Although there are slight differences, the bars are fairly similar in height. This tells us that the dataset is reasonably balanced across different cities, which is important because it prevents one city from dominating the analysis. plt.figure fixed size is equals to 8,6 new figure using Matplotlib. The width of the graph is set to 8 inches and the height to 6 inches. Then using Seaborn's bar plot function. A bar plot is used to compare the average value of a numerical column across different categories. Here, x is equals to city places the different cities on the x-axis, while y is equals to price plus the average house price for each city on the y-axis. Data is equals to df parameter tells the Seaborn to use our data frame, and color is equals to red simply changes the color of all bars to red. Then I am adding a title to the graph so that anyone viewing it immediately understand that we are comparing house prices across different cities. plt.xtext rotation is equals to 45. Here I am rotating the city names by 45 degrees. This prevents the labels from overlapping and makes them easier to read. plt.show displays the graph on the screen. Now let's interpret the visualization. On the x-axis, we have different cities, and on the y-axis, we have the average house price for each city. From this graph, we can observe that the average house prices across all cities are quite similar. There are no huge differences between them. Among these cities, Delhi, Mumbai, and Kolkata have slightly higher average prices, while Chennai has a comparatively lower average house price. However, the differences are not very large, which suggests that house prices in this dataset are fairly balanced across different cities. The small black lines on top of each bar are called error bars. They show that the variation or uncertainty in average price. Since these error bars are also similar in size, it indicates that the price variation across cities is relatively consistent. Again, plt.figure fixed size is equals to 8,6. Fixed size 8,6 sets the width of the graph to 8 inches and the height to 6 inches. Next, I am using Seaborn scatter plot function. A scatter plot is used to study the relationship or correlation between two numerical variables. Here, price is placed on the x-axis and the locality rating is placed on the y-axis. Each blue dot represents one house in our dataset. The data is equals to df parameter tells Seaborn to use the data frame named df. Then I am adding a title to the graph so it's immediately clear that we are analyzing the relationship between locality rating and house price. Finally, plt.show displays the scatter plot on the screen. Now let's analyze the graph. On the x-axis, we have the house price. On the y-axis, we have the locality rating, which ranges from 1 to 10. Each blue dot represents a single house. If there were a strong positive correlation, we would expect the points to form an upward sloping pattern, meaning higher rated localities would consistently have higher prices. If there were a strong negative correlation, the points would slope downward. However, in this graph, the points are spread across almost every price range for each locality rating. This tells us there is no strong linear relationship between locality rating and house price in the dataset. In other words, our higher locality rating does not always mean a significantly higher house price. This suggests that other features like area, number of bedrooms, furnishing status may have a greater influence on house price than locality rating alone. Next, we will create a correlation heat map to analyze the dataset. Here, we used sns.heatmap to create a correlation heat map. Here, df.core calculates the correlation between all numerical columns in the dataset. The numeric only is equals to true. Parameter tells Pandas to ignore text columns like city, furnishing, and calculate correlation only for numerical data. The n0 is equals to true. Parameter displays the actual correlation values inside every cell, so we don't have to estimate them for the colors. The cool warm color map uses blue shades for lower or negative correlations and the red shades for higher positive correlations, making the relationships easy to identify. The correlation value ranges from -1 to +1. A value close to +1 means a strong positive relationship, meaning as one variable increases, the other also tends to increase. A value close to -1 means a strong negative relationship, and a value close to 0 means there is a little or no relationship between the variables. Looking at our heat map, we can say that bedrooms have higher positive correlation with price, around 0.59. This means houses with more bedrooms generally tend to more expensive. area also has a positive correlation of about 0.33, showing that the larger houses usually cost more. Bathroom, stories, and locality rating have weaker positive relationship with price. Age has a very small negative correlation with price, around minus 0.05, which means it has almost no effect in this dataset. Overall, this heat map quickly helps us identify which features are most important for predicting house prices. We perform exploratory data analysis using Python. We explored dataset, we visualized important patterns, found relationships between different features. These insights help us to arrive at a better outcomes that would help us to train better machine learning model. If you found this video helpful, don't forget to like and subscribe my channel. Follow the journey and let's become data scientists together.